Hello, am I audible?
Yes, sir.
Yes, sir.
Okay. So in the last class, I left a numerical. The question was V is k t to the power 2 by 3, right? You're supposed to calculate the work done. So the question was V is k t to the power. It was 2 by 3 or 3 by 2?
2 by 3.
2 by 3. 2 by 3. You're supposed to calculate work. Now, this V is k t to the power 2 by 3 is not an equation of any standard process. The standard process that we have is maybe isothermal, it could be adiabatic, it could be isobaric or isochoric. This equation will match with none of them. So to calculate work done, in this type of cases, you have to derive it from the initial. So what is how we calculate work done? The formula of work done is integral of PdV from V1 to V2. So you have to derive the work. See, these type of questions are common in JEE exams. Sometimes it gives you an equation and that equation will not match with any of the standard process. Like it won't be adiabatic, it won't be isothermal, it won't be isochoric, it won't be isobaric. So in that case, what you will do is V is kt to the power 2 by 3. You need pressure. So to get the equation of pressure, you can use this equation PV is equal to nRT. Then you can write this as in this way, right? P is equal to its nRT divided by V. So when you do this substitution, the work done will comes out to be its integral of its V1 to V2. Instead of P, we can substitute its nRT divided by V into D. Now, there is one small problem. This integral have two variables. One is temperature and another is volume. So what you will do, you will substitute it. Like you can substitute V as kt to the power 2 by 3. So instead of V, you can write it's nRT by V. Instead of V, I'm writing some k t to the power 2 by 3. And then it's T. Limit is also given. The question, the limit was the work done when temperature changed by 90 Kelvin. So the limit is given in terms of temperature. So the limit is given from temperature T1 to temperature T2. This integral is still not solvable. Adil, can you tell me what's the problem with this integral? It's still not solvable.
So because dV.
Yeah, you have T, so you should be having dt, but there is one dV. So we can take this constants outside, like I can bring this nr by k outside. We are left with just T1 to T2. It's T to the power 1, T to the power 2 by 3. It's T to the power 1 minus 2 by 3 into D. So now we have to substitute dV in terms of dt. So what you can do is, see, this is V is k t to the power 2 by 3. If you want, you can write this as, just differentiate this with respect to temperature dV by dt. So dV over dt will be k, it's 2 by 3, t to the power 2 by 3 minus 1, that will be minus 1 by 3. So from here, you can write that your dV is, it's 2 by 3k t to the power minus 1 by 3 into dt. Now what you can do is, you can just substitute it here. So your work done will be, it's nr by k It's T1 to T2. 1 minus 2 by 3 means T to the power 1 by 3. dV is 2 by 3K T to the power minus 1 by 3 dt. Now see, this is dt. This K will cancel this K. 1 by 3 power and minus 1 by 3 power will get cancelled out. So you are left with only W is NR. This is 2 by 3, which you can bring outside. It's T1 to T2. dt, the integral of dt is t. Or so it's dt. So if you can even integrate it, your work done will be 2 by 3 NR. When you integrate dt, this comes out to be T2 minus T. And this T2 minus T1 is given in the question, it's 90 gram. So this is how you will calculate work done if the equation does not match with any of the standard processes. Please note it down. Just one more small topic, which is heat engine and then refrigerator, and then we'll start with the modern physics. So modern physics is very easy, very scoring. We will get plenty of questions on modern physics also. Pradarshini, Krishna, is it clear?
Yes, sir.
Yes.
See, KTG, thermal and thermodynamics means 3 to 4 questions. Rehan, are you getting these calculations?
Yes, sir.
Ashrit, you were there in the last class, but your audio was not connecting, right? Just tell me once you have written. We'll start with the heat engine and refrigerator. There's small topics, 2-3 relations, and then move on.
So should we solve this further or?
Yes, you will substitute the value of n which is given in the question. If nothing is given, then take it to be 1 mole. Put the value of gas constant. T2 minus T1 is 90. Can I scroll if you have written?
So I have a doubt, sir.
Yes.
So how do you differentiate adiabatic and isothermal graphs, sir?
Okay, the same thing. This was the equation of PV to the power gamma is equal to constant. So when I differentiate P, what is the derivative of P with respect to P? This one, right? Now
Yes,
it's a partial derivative. So what you can do is when you differentiate P with respect to it comes out to be 1 and you will put dPA. You are differentiating two variables simultaneously. So when you differentiate P, you write dP. And when you differentiate V to the power gamma, you will write D. So it's V to the power gamma plus. Then what you will do is you put P as it is. Derivative of gamma V to the power gamma is gamma V to the power gamma minus. And then you will put a dV. And in the right hand side, you have a constant, so derivative would be 0. Yes, Krishna, clear?
No, sir, I'm saying like when the graph is given, like how do we tell which is isothermal and which is
Okay,
adiabatic?
just by the slope. So when you do the differentiation, you will get dP by dV. For the adiabatic process, you will get this will be minus gamma P by. And if you do when you do the same thing for isothermal process, this is minus P by. Now, can you compare the slope of the adiabatic and the slope of the isothermal? Whose slope is greater? Which one have a greater slope? Gamma P by
Adiabatic.
V or P by adiabatic? Both are negative. This gets multiplied with gamma, which is greater than, so it's more negative. So here you can say this here, this is here slope is greater as compared to this point. Is it clear up to here, Krishna?
Yes, sir.
So greater slope means your curve will be steep. So if I draw this as the graph of the isothermal, for adiabatic it will be steeper. Slope is more, so it will be steeper. Like if I give you two straight lines, I give you one this and another this line, which will have a greater slope, line 1 or line 2?
Line 1.
Line, if it is steep, it's slope, just by the steepness. Okay, so now let's move on to the heating. Carnot heating. See, every heat engine have three essential parts. One is the source. Source is that place where the burning of the fuel happens. You can take any engine. If you take an engine of a car, then source means the fuel tank. Fuel burns in the fuel tank. So that is the source of the engine. So every engine have a source that have a working substance. In a petroleum engine, the working substance is the petroleum vapor. In a steam engine, the working substance is the steam. The steam moves the pistons. In steam engine, the working substance is steam. Then you have sink. Sink is that place where your engine will reject the heat. So for almost all the engines, the sink is the environment. So every engine rejects its unused heat, or you can say it's a wasted heat, to the sink. So if you take a simple engine, let's discuss about the steam engine. So the simplest steam engine could be you take some water in a kettle, you heat up the kettle. When the kettle gets heated up, steam generates, and that steam can open the lid of the kettle. So that is the simplest engine that we can say. So here, steam is doing the work. Steam will lift the lid of the kettle. So we'll say that steam is the working substance. It takes heat from the source. So the burner from which maybe you put it over a gas cylinder. So the gas cylinder is your source from which your engine is absorbing heat. And the remaining part of the heat gets wasted in the surrounding. So the surrounding will work as a sink. So for any heat engine, the working substance takes some heat from the source. It absorbs some heat from the source. Out of this heat, it performs work done. So it converts some part of this heat into work done. If an engine is converting 100% of Q1 into work done, then we would say that efficiency of the engine is 100%, which is not at all possible. That is the second law of thermodynamics. Second law of thermodynamics says efficiency of an engine can never be 100%. It cannot convert 100% of heat into work. So Q1 is the heat that engine absorbs from the source. Out of this Q1, it will convert some part to the work. So the engine is converting 50% to the work. Then you will say, okay, the efficiency is 50%. The remaining part of the heat gets rejected to the sink, which is Q2. A simple working of it. And the difference between the heat absorbed and the heat rejected is the work. Now, in these heat engines, if we want to build an ideal heat engine means an engine which have the maximum efficiency. And remember that efficiency can never be 100%. It will always be less than 100%. So we're talking about an ideal engine which can have maximum efficiency for two temperature range. One is the temperature of source, another is the temperature of sink. So for all our calculations, we will consider T1 as the temperature of the source and this T2 as the temperature of the sink. So Aditya, which one should be higher, T1 or T2? Which one of these temperatures should be a high temperature, T1 or T2? Aditya, good. Ashrit? Yes, Aditya, saying something.
T1, sir.
T1, source, the temperature of source is higher and sink is lower. So for this temperature range, the engine which can give you maximum efficiency is known as Carnot heat. And again, is an ideal heat engine. Why is ideal heat engine? Because source, working substance, and sink in a Carnot heat engine are ideal. Means you have a source which have infinite heat capacity. Finite heat capacity means you can extract any amount of heat from the source and its temperature will not change. Sink have infinite heat capacity, means you can reject any amount of heat to the sink, but it will not, the temperature of sink will not change. Working substance is an ideal gas. So you're taking everything to be ideal. That's why we call this as an ideal heat engine. Now this ideal heat engine is also known as Carnot heat engine. The reason is Carnot heat engine works on a particular cycle, which is known as Carnot cycle. So what does Carnot cycle mean? See, when a heat engine works, it works into a cycle. Cyclic process we have already discussed. Cyclic process means the initial and the final state of the system would be same. So here, this is the cycle which is known as Carnot cycle. Means your engine, this is the initial state, A point. This is the initial state. Here pressure is V1, volume is V1, temperature is T1. Then you expand your ideal gas isothermally. We know that in isothermal expansion, temperature will remain constant. But when a gas expands, what happens with the gas, Marita? If a gas expands, what happens with the gas? Its temperature should remain constant or its temperature should decrease, Marita?
So when it expands, its temperature should decrease.
Why? Why it should decrease? You're right, its temperature should decrease. I'm asking for the reason. Why the temperature should
Internal energy decreases.
decrease? Priyadarshini, why the internal energy decreases when a gas is expanding? The reason is gas is expanding. That means gas is doing some work. The gas is doing work at the cost of its kinetic energy. Sorry, internal energy. The internal energy of the gas is getting converted into the work. That's why the temperature decreases. Now, you want the process to be isothermal, means you want its temperature to remain constant. So what you will do, you will provide some energy from the outside source. So your engine or your working substance will absorb some heat energy. So this energy Q1 is absorbed by the Carnot engine during isothermal expansion. That's important. Next, you expand this gas using adiabatic expansion. Means temperature will not change. Pressure here is P2. Then pressure becomes P3, volume becomes P3, temperature becomes T2. Because it's adiabatic, so temperature changes. Now you want to bring back the system to the initial state. So earlier, initially you expanded it, then you will compress it. Then you compress your gas, isothermal compression will come here. Then you'll compress it further, it will come here. This is the adiabatic compression. It will come back to its initial state. So this is the Carnot cycle. This order is very, very important. Isothermal expansion, adiabatic expansion, isothermal compression, and then lastly, adiabatic compression. When you calculate work done for the entire process, it comes out to be Q1 minus Q2. Efficiency of the engine means work done per cycle divided by heat absorbed per cycle. Work done from here, you can write Q1 minus Q2 by Q1. See, you can write this as the Q1 by Q1 minus Q2 by Q1. So that will be 1 minus Q2 by Q1 is efficiency. And Q2 by Q1 here in Carnot cycle, it can be proved that Q2 by Q1 is equal to T2. So you can write this as 1 minus T2 by T1. Another important thing, while you are calculating efficiency, always take your temperature in Kelvin. Always take your temperature in Kelvin when you are calculating the efficiency. Please note it down. We'll do refrigerator and then we will do numerical. Ashrit, Aditya, are you getting it?
Yes.
Pridarshini, is it clear? This scarlet region?
Yes.
Okay, did you people get your admit cards for JEE?
No, sir.
No, sir.
No, sir.
Tell me once you have written. We'll start with refrigerator. Rehan, is it clear?
Yes, sir.
Okay, once this JEE crash course gets over after your JEE exam, you can start preparing for other exams. Like you can start preparing for CUET. You can prepare for Carnatic engineering exams, BitSat if you have applied, Vellore if you have applied. So we'll extend this batch. After the JEE exam, we'll convert this batch to CUET and for other engineering exams. Can I scroll if you all have written?
Just a second.
Okay, Adrian, if I asked you to calculate work done from the for the portion AB of the graph, how will you calculate work done for the portion AB? Yes, Adrian. If I ask you to calculate work done for the portion AB of the graph, how will you calculate work?
So work done for the isothermal expansion.
Yeah, it will be the work done for that. You can get these type of questions in your exam. It will draw this Carnot cycle and ask you to calculate work done for different. So just isothermal and adiabatic, the formula will be same, the formula that you did in isothermal process. Tell me once you have written answer. In the last test, Adriel and Marita performed very well. So I may be arranging some extra classes for them for two more topics. So anyone can join those classes, but I will recommend to only those who are performing in the test because it's for JEE exam by studying very limited portion of the syllabus, you can score very well. By studying 100% of the syllabus, still there are chances that you can't even score 30%. So whatever you do, that portion should be very, very strong. I'll be arranging some more classes for the topic which are not mentioned in the schedule. Can I scroll it now?
Yes, sir.
Sure. So the syllabus for the test that's going to be held on this Friday will be KDG and thermodynamics, photoelectric effect that we will finish today. Dual nature, de Broglie hypothesis, that topic also will finish today. And with from Amna ma'am side, it would be capacitance, current electricity, DC circuit. Aditya, written.
Sir.
Aditya, did you apply for this CUT exam?
Yes, sir.
Written. I hope everyone have it. So let's do this question. So this is from JEE Pvt 2021. Reversible engine has an efficiency of 1/4. Remember one thing. You in your syllabus, there is only one type of engine, that's Carnegie. So whatever he says, talking about Carnegie. So efficiency is 1/4 if the temperature of the sink is reduced by 58 degrees Celsius. So efficiency is, the formula efficiency is 1 minus T2 by T1. Rehan, T2 is the temperature of sink or source?
Think.
Sink. So efficiency is 1/4. You can say 1/4 is 1 minus its T2 divided by T. That's my first. And the second equation is saying if the temperature of the sink is reduced by 58 degrees Celsius, efficiency becomes double. So Rehan, can you just tell me what will be the new efficiency? Rehan, just read this question and tell me after this line, what will be the new efficiency that I should take? Pradarshini, what will be the new efficiency here?
1/2, sir.
1/2. It's doubled. Earlier it was 1/4, so now it's double of 1/4. So that will be 1/2. It's 1 minus. Aditya, what will be the temperature of the sink now? Earlier it was T2. What is the temperature of the sink now? In the second part of the question. Pradarshini. Yes, Aditya, you're saying them. What is the temperature of the sink now? Pradarshini?
It'll be T2 minus 58.
T2 minus 50. You're saying that the sink is reduced by 50. It's T2 minus divided by T. You need temperature of the sink. So what now you can do is you can just divide these two equations. When you divide them, your T1 will get cancelled out. So I'm not solving the complete question, but this is the type of question that one can get answered. Note it down. We'll do refrigerator and we'll do one question.
So should we substitute, give 58 in terms of Kelvin?
Well, here is the difference, man. So if you are taking it in degree Celsius, will come in degrees. But yes, you're
Okay,
saying
sir.
you are right.
Okay.
You are right. You are right. You are right. No. It would be better if we convert this into Kelvin. It will always be better if we convert this. So this is 273 plus 58. So how much is it? 273 plus 58. 11. 13. 3. Yes, it's always better if you convert everything in Kelvin. Your answer will come into Kelvin and again convert it. So I'm not doing the complete calculation. You can divide these two equations and you get the value. So you have two equations in two variables. You can use substitution. If you have written it, can we move on to the next topic? Aditya, clear now? I hope you all have written. Let's move on to the next topic. The next topic is the refrigerator. So refrigerator, or this is the same theory is applicable for air conditioning. So it is again a Carnot heat engine, but it's working in reverse direction. What happens? Usually a Carnot heat engine takes heat from the source and reject it to the sink. Refrigerator do the opposite thing. It takes heat from the sink and reject it to the source. So for a refrigerator, sink is the food stuff which is placed inside the refrigerator. You can say space inside the refrigerator is sink for a refrigerator, and the surrounding is source. So what it do? It takes heat from the sink, means from inside the refrigerator, and reject it to the source outside the refrigerator. So this is the refrigerator. This is sink region inside refrigerator. This is source, the environment. So this refrigerator takes some heat from the sink, which is at lower temperature, and reject it to the source, which is at higher temperature. Now, there's again one statement of second law of thermodynamics, which says a self-acting machine cannot transfer heat from low to high temperature. See, T2 is low temperature, T1 is high temperature. So this refrigerator is basically transferring heat from low to high temperature, which is not at all possible for a self-acting machine. So here you have to do some work on the refrigerator. That's why you have to connect your refrigerator with the power supply. Through power supply, the compressor of the refrigerator is doing work on the refrigerator. And due to that work, your heat get transferred from sink to source. So this is the work done by the compressor. So here work done is again Q1 minus Q2, just like the heat engine. The heat emitted to the source minus the heat absorbed from the sink. So Q1 minus Q2. Here, instead of efficiency, we don't use efficiency here. We use coefficient of performance. Coefficient of performance is heat absorbed from the sink, means this heat absorbed from the sink, divided by the work. This is known as the coefficient of performance. Greater the value of beta, greater would be your refrigerator. See, efficiency can never be greater than 100%. Efficiency will never be greater than 1 if you're taking it in fraction, but your coefficient of performance can have any value. It can be 10, it can be 20, it can be 30, it can have any value. So heat absorbed from the sink is Q2, work done is Q1 minus Q2. So I can write this as Q2 by W or Q2 by Q1 minus Q2. Or if I convert this in terms of temperature, it comes out to be T2 by T1 minus Q2. And this is the relation between the coefficient of performance and the efficiency of it. Beta is 1 minus beta by 2. This is your refrigerator. Please note it down. I'm going to do one more very good one. Yes, written.
Yes, sir.
Okay. So let's do one question on refrigerator, then this is all. Everyone have written up to here? Rehan, Aditya, Marita.
Yes, sir.
So do this question. Answers. See, it should not take more than 2-3 minutes. Easy question. Whenever power is given, power is given in watts. That means you have energy or work that is given for 1 second. So if 35 watt is the power, that means this is the work done that the power supply or the compressor do on the engine. Oh, okay, Krishna. So this 35 watt is the power. Power means work done per unit time. So this is work done in 1 second. Rehan, out of minus 10 degrees Celsius and 25 degrees Celsius, which one is T1 and which one is T2? Aditya, which one is T1 and which one is T2 out of minus 10 degrees Celsius and 25 degrees Celsius? Pradarshini? Pradarshini, which one is T1 and which one is T2 out of minus 10 degrees Celsius and 25 degrees Celsius? Yes, Aditya, you're saying something.
Minus 10 is T1.
Minus 10 is T2. Lower temperature is T2. And 25 is T1. Answers? Adriel, Marita, Pradarshini, did you get any answer? Just one more minute and we'll start solving. Yes, Pradarshini, can you tell me the formula of this coefficient of performance in terms of temperature? Beta in terms of temperature.
So 1 minus T1 by T2.
T2 by T1 minus
T1.
T1 minus T. So how much is T2 here, Pradarshini? So the value of T2 here?
T2 is minus 10.
Minus 10. So convert this in Kelvin. How much is it? This one in Kelvin? 263, right?
263, yeah.
25 degrees Celsius. This is T1. How much this in Kelvin?
298.
298 minus T2, which is 263. This is your beta. So this will be 263 divided by, how much is this thing? 298 minus 63, it's 5. And then 3, 35. Aditya or Rehan. Rehan, are you in class? Okay, Rehan, can you just tell me formula of coefficient of performance in terms of Q2 and W? Formula for the same, for in terms of heat which is absorbed from the
Q2
same
by-
and Q2 by W. So Q2 you're supposed to calculate. W is the heat, the power consumed, 35 volt. And remember, this is in 1 second, so that's 35. You can equate these two. So when you equate these two, you get Q2 divided by 35, which is equal to 263 divided by 35. It's cancelled. So Q2 comes out to be 263 joule per second. Because we use this W in watt. Watt means 1 second. So that's why this is joule per second. First answer. Adriel was getting the right answer. Right. Okay, so that was about thermodynamics. Let's start with modern physics. Rehan, written.
Yes, sir.
Let's start with the next. The next is in modern physics, we have 3 chapters basically. The one is photoelectric effect and dual nature. Another is atom, and then we have nuclear. And this is the most scoring portion of your syllabus. From modern physics, you will get 3 to 4 questions. And if you just practice, you can attempt all of them. They're really very, very easy questions. So before starting anything, let's start with the basics of photo. So I'm starting modern physics. So in modern physics, you have 3 chapters. First is dual nature. Second is atom. And third is nuclear. So we'll start with dual nature. So before starting dual nature, there are a few general concepts of photon theory that one should know before starting. The first is Planck quantum theory. So Planck quantum theory basically says if you have a source of light, then the radiation coming from that source is not continuous. Means if you have a bulb in front of you, the light coming from the bulb is not continuous. It consists of packets of energy. There are certain packets which are coming with a very, very high speed. So one packet is coming with some speed, then another packet is coming at some speed, and the speed is c, which is speed of light. 3 into 10 raised power 8 meters. And the energy of each packet is decided by its frequency. This packet is known as photon. So Planck says that radiation is not constant, continuous. It has packets of energy. Later on, we call those packets of energy as photon. The energy of each photon is given by this expression. It's Planck constant multiplied by frequency. Nu is frequency of radiation. So if you want, you can relate frequency and wavelength also. You can write frequency as hc by lambda. So this is the expression of energy. There's one more thing. The unit of energy that we'll use here is an electron volt. We don't use joules here. So 1 electron volt is 1.6 into 10 raised to the power minus 19. That's 1 electron. So you always need energy in electron volt, not in joule. So, and H is Planck constant. The value of H is 6.626 into 10 raised to the power minus 34 joule seconds. This lambda wavelength here is usually given in angstrom or in nanometer. So you should remember this thing that one angstrom is 10 raised to the power minus 10 meter. 1 nanometer is 10 raised to the power minus 9. So you have 1 angstrom and you have 1 nanometer. 1 angstrom is 10 raised to the power minus 10 meter. 1 nanometer is 10 raised to the power minus 9. So if you want to convert nanometer into angstrom, so 1 nanometer is 10 angstrom. So that was Planck quantum theory. That energy is in the form of radiation, h nu, and the energy, radiation is not continuous. It consists of packets of energy. Those packets are known as photon. Energy of each photon is h nu, or it's hc by lambda. Another thing is, if you take this expression, see, if I give you wavelength and I ask you to calculate energy in electron volt, that's a lengthy calculation. See, you will put h equal to 6.626 into 10 raised to power minus 34. Then you will put the speed of light 3 into 10 raised to power 8 meter per second. Then you will substitute the value of lambda. It will comes out to be in joule. Then you will divide it by 1.6 into 10 raised to power minus 19 to convert into electron. What you can do directly is, instead of hc, just substitute 12400 and take your wavelength lambda in angstrom, and your energy will be in electron. So from now onwards, instead of using hc by lambda, I'll be using this term. So it will just cut down some steps of the calculation. So just put your wavelength into lambda, you will get your energy in electron. After this, so this is energy. From here, you can calculate mass of photon also. Mass of photon you will do. So Rehan, what is the rest mass of photon? How much is the rest mass of photon? Adrian, how much is the rest mass of photon? Mass of photon when they are at rest? Open question. Does anyone remember how much is the rest mass of photon? 0.
1.6 and 10 raised to minus.
Photon. So if you have photon and they
Okay,
are at
okay.
rest, then their rest mass of zero. But photons gain mass when they start to move. So if you want to calculate the moving mass of photon, then I have to introduce one more one. Okay, have you heard about Einstein's mass energy equivalence? Einstein mass energy. Aditya, have you heard about Einstein mass energy equivalence?
Sir.
Yes. What is Einstein's mass energy equivalence? Please explain. Do you remember the relation, the mathematical formula?
Oh, sir, that E is equal to mc square.
E is equal to mc square. So this relation says mass is not conserved. Mass is not conserved. It can be converted into energy. So if you have m amount of mass, and if somehow that mass get disappeared, like the thing this happens in your atomic bomb and hydrogen bomb. So if your mass get disappeared, it will convert into energy, and the energy will be m into c square, where c is speed of light. Similarly, energy is not conserved. If you have some amount of energy and suddenly that energy gets disappeared, that means that energy is converting into mass. So mass corresponding to energy is E by C square. That's Einstein's mass energy. So this mass energy equivalent simply says neither energy is conserved nor mass is conserved, but they can convert from one to rest mass of photon is m naught, which is equal to 0. But when photons move, they gain some mass. So moving mass of photon is m. Moving mass of photon is equal to m. So to get the value of this moving mass, what you can do is you can just equate these two equations, h nu and mc square, because both are energies. So when you equate them, mc square is equal to h nu. mc square is equal to h nu. You get m, which is h nu by c square. h nu by c square. This is m, that mass of photon. This is h nu by c square. After mass of photon, the next is you can calculate momentum of momentum. Rehan, how you calculate momentum? What's the formula for momentum? Aditya,
equal
yeah,
to mv.
yeah, mass into velocity. So momentum is mass m into speed c. Mass m you can write, this is h nu by c square multiplied by c. So this c will cancel this c, and this is equal to h nu by c. This is the momentum of photon, h nu. Note it down. You'll see what type of questions you can get from this just by the concept of photon. So if you combine class 11th and 12th syllabus, these three chapters are most for you. So if your thermodynamics, KTG, and modern physics are very strong, that means out of 25 questions of physics, you should be able to solve at least 6. And as we have discussed in the initial classes, if you can score out of 75 questions, if you can attempt 25 questions and they are correct, that means you'll have a very good percentage, something around 94. Tell me once you have written slowly. Can I scroll it now?
Yes, sir.
Okay, after this, there's one more term which is intensity. Basically, there are two terms. One is power and another is intensity. You should name both of them. So the next term is power. See, power is energy by time. It's energy per unit time. Huh? It's energy per unit. And the SI unit of power is what? Then you have another thing which is intensity. See, intensity is power per unit area. So intensity is power divided by it. So intensity is power, which is energy. Per unit area. Per unit. So this is intensity, energy per unit area per unit. The unit of power is it's watt per meters. So to solve questions which are just based on photons theory, you should know these terms. Just note it down. We'll do one question. Question which will be using only this concept. Okay, let's solve this question. See, 2 megawatt laser. Rehan, what does 2 megawatt means? 2 megawatt laser. What does 2 megawatt means? Is it power, intensity? What is or energy? What is 2 megawatt? Yes, Pradarshini, what is 2 megawatt here?
Power, sir.
Power. So here the power is given as 2 milliwatt. Sorry, small m is milliwatt. So that's 2 into 10 raised to the power minus 3. Or which you can write this as, this is 2 into 10 raised to the power minus 3 joule per second. So this is the energy emitted by your laser in 1 second, 2 into 10 raised to power minus 3. At a wavelength of 500 nanometer. So the lambda is 500 nanometer. So it's 500 into 10 raised to the power minus 9. The number of photons that will be emitted per second. So energy of one photon can be written as hc by lambda. This is energy of one photon. So here everything is given in joules. So we will not be using that 12400 thing. So this is energy of one photon. And you have to calculate number of photons in this. So this is just a unitary method. So the number of photons will be simple unitary method, nothing else. Number of photons will be the power that is emitted by the light or the bulb divided by the energy of one photon. So it's power divided by energy of one photon, which is hc by lambda. So this lambda will go to numerator. Next, what you can do is you can substitute the values. How much is power? Power is 2 into 10 raised to the power minus 3 multiplied by lambda. How much is lambda? It's 500 into 10 raised to the power minus 9. Divided by h, which is 6.626 into 10 raised to the power minus 34. C is 3 into 10 raised to the power. So this is the number of photons that are emitted by it per second. This is in 1 second. Now, in the same question, if he asks you to calculate number of photons emitted in 1 hour, so Marit, how will you calculate number of photons which are emitted in 1 hour? These are the number of emitted photons in 1 second. How will you calculate photons emitted in 1 hour?
Into 3600.
Right, into multiplied by the time seconds corresponding to it. Just note it down. Is it clear? Rehan, Pradarshini?
Yes.
From basic photon theory, you can get these type of questions. Okay, then good. Next is de Broglie happens. De Broglie happens. So de Broglie hypothesis introduced the concept of matter wave. It introduced the concept of matter wave. So matter wave is simply wave associated with a matter. So de Broglie says that matter have dual characteristic. Means if you talk about this pen will have both particle as well as wave characteristic. So the wave associated with this pen is known as matter wave. And if you want to calculate the wavelength of that matter wave, that is given by de Broglie hypothesis. So if you have a body of mass, it's moving with the momentum. Then the wavelength associated with this particle is given by h by. This is the de Broglie hypothesis. Now, this is the basic formula. Now you can convert this h by p into many forms. Like you can write this as lambda is h by p, p is momentum. So you can write momentum in terms of kinetic energy also. So you can write that momentum is twice of mass into kinetic energy. So this way you can express it in terms of kinetic energy. So this is twice of mass into kinetic. If you want, you can convert this expression in terms of potential difference also. So what you can do is, instead of kinetic energy, you can substitute QE. So you can write this as charge multiplied by potential. So kinetic energy can be written as Q, where V is the potential. If you want, you can write this as one more form. You can write this in terms of temperature also. Like kinetic energy can be written as 3 by 2 Boltzmann constant. So this expression can also be written as in terms of temperature. 3m Boltzmann's constant into temperature. So you should remember all these expressions. Now, if you want to calculate de Broglie wavelength for an electron, if you are calculating precisely for an electron, then what you can do is, here you can use this expression. Lambda is h by 2mq. So if you are using for an electron, h is known, mass of electron is known, charge of electron is known, only v is the variable. So you can write this as 6.626 into 10 raised to the power minus 34 divided by root over twice of mass of electron, which is 9.1 into 10 raised power minus 31, you can write. Multiplied by the charge of electron, which is 1.6 into 10 raised to the power minus 19, multiplied by V. So when you solve this, this comes out to be, it's 12.27 by root V angstrom. So when you are calculating the de Broglie wavelength of an electron, you need just potential. If potential is given, V is the potential. So if potential is given, you can calculate de Broglie wavelength of the electron. Note it down, we'll do one question over it. And just one more thing, one last. Experimentally, this was, do you remember the name of the experiment which confirmed this de Broglie hypothesis? First experimental demonstration of de Broglie hypothesis? No, it's Davison and German.
Davidson.
You should remember this. It was Davison and German experiment. So Davison and German experiment is the first experimental proof of the de Broglie hypothesis. Remember the name of the experiment. No, very good.
Sir, is the kinetic energy under the root or outside?
It's under root. Kinetic energy is under. Yes, written.
Yes, sir.
Okay, the next is. See, there are two types of questions on de Broglie hypothesis. The easier question will be using only lambda by h by. So they are very easy questions. I'll give those type of questions in homework. And there is one more class of question which are related through mechanics. Like we know that lambda is h by p now. This is h by p. And what is p? P is mv. So while calculating this velocity, it can use any portion of mechanics. There's 2-3 portions which are very frequently used. The one is collision. It uses the concept of collision. Then it sometimes use the portion from magnetics also. Like in magnetics, if you can remember, if charge particle is moving perpendicular to magnetic field, then you have expression for radius of the charge particle. You have expression for the velocity of charge particle. So from that expression, he can ask you to pick the value of velocity and then you put that value in. So if he's making an easy question on de Broglie hypothesis, that will be related to lambda is h by p or h by 2mqv only. But if he's making a tough question and can relate it to mechanics, usually in mechanics will relate it to collision, or it can relate it to magnetics. In magnetics, it will relate it to path of charge particle. So this question is related to collision. So you have a particle A of mass ma, which is m by 2. moving along the x-axis with velocity v0, collides elastically with another particle at rest having mass m by 3. So the collision is elastic. When I say that collision is elastic, that means kinetic energy is conserved, or you can also say that coefficient of restitution is. If both particles move along x-axis after the collision, the change in delta lambda you need in de Broglie wavelength of particle in terms of de Broglie wavelength lambda before. So before and after collision, the momentum of the particle will change. Momentum will change. That means de Broglie wavelength will change. So it's supposed to calculate the change in de Broglie. So you have particle A, particle B is at rest. So this is particle A. Its mass is m by 2. It's moving with velocity v0. It collides with particle B. Its mass is m by 3. This is at rest, so its velocity is 0 meters. After collision, this is particle A. A will have some velocity, which is not given. So let's say the velocity of A is v1. B will also have some velocity, and let's say that velocity is some v2. This is velocity. So I need wavelength of A before collision, initial wavelength of A before collision. So, Rehan, what will be the wavelength of A before collision? De Broglie wavelength of A initial. Pridarshini, what is the initial wavelength of A before collision?
It will be h by m by 2 into v naught.
H by m by 2. That's possible. Final wavelength of A after collision will be h by m by 2 into v. Now the problem is this v1. You have to calculate this v1. There are direct formulas also from where you can calculate this v1. But if you don't remember, don't memorize that formula, you can do it by conservation of momentum and conservation of kinetic energy. So I'm doing it by conservation of momentum and conservation of kinetic energy. So in this question, you will learn conservation thing also. So let's apply conservation of momentum. Conservation of momentum. So conservation of momentum says initial momentum before collision is equal to final momentum. The momentum before collision is equal to momentum after collision. So this is before collision and this is after. So before collision, momentum is m by 2 v0 plus this is m by 3 into 0, so that will be 0. After collision, it's m by 2 v1 plus the mass of B is m by 3, so it's m by 3 v2. That's my first question. So what you can do is you can just cancel m from here. M will get cancelled. So from this equation, you can calculate V. See, there's two variables, V1 and V2. You need another equation that can come from conservation of kinetic energy. This equation can come from conservation of kinetic energy. Second. So this is conservation of kinetic energy. Conservation of kinetic energy is initial kinetic energy, which is half into m by 2 into v naught square. Kinetic energy of the second particle is at rest, which will be 0, which is equal to half m by 2 v1 square plus half m by 3 v2 square. So if you want from equation 1 and equation 2, you can get the value of V1 and V2. But it will be very lengthy. Like if you are solving this equation, it will take 3-4 steps. So you can save some time. Instead of using conservation of kinetic energy, what you can do is you use coefficient of restitution. So for a collision, coefficient of restitution is relative velocity of separation divided by its relative velocity of approach. So it's relative velocity of separation divided by the relative velocity of approach. So relative velocity of separation is this one. So after collision, they get separated. So it's V2 minus V1 is the relative velocity of separation, which is V2 minus V1. Relative velocity of approach is this term. Velocity of A minus velocity means V0 minus 0. And if collision is elastic, that means E is equal to 1. For elastic collision, this instead of E, you can substitute 1, which is V2 minus V1 divided by V0. So you can say that V2 minus V1 is equal to V. Or you can say that your V2 is equal to V0 plus V. V0 plus. Now, instead of the value of this V2, you can substitute it here in the conservation here. So this thing, so it's a lengthy problem. If it connect this with mechanics, it's a very lengthy problem. So you can substitute 3 in 1. When you do this substitution, see this is, it's V0 by 2 plus 0, which is V1 by 2 plus V2 by 3. 0 is equal to V1 by 2 plus V2 by 3. So instead of V2, you can write V0 plus V1 by 3. V1 by 3. So this is V0 by 2. In the right hand side, you can take LCM. So when you take LCM, it comes out to be 6. So this is 3V1 plus 2V0 plus 2V1. So this 2 will cancel this term. This is 3. So this is 3V0, which is equal to 3V1 plus 2V1. It's 5V1 plus 2V0. So 3V0 minus 2V0 is V0. So you can write that V0 is equal to 5. So finally, you have V1, which is V0 by 5. So if you have V0, that V1, that means you have final wavelength of A also. Final wavelength of A is h by mass of A, which is m by 2. Which is m by 2 into velocity, which is V0 by 5. This is 10, it will come to numerator. So you have 10 h by mv. And your initial wavelength of A is, it's h by m by 2 v. m by 2 v. The 2 will go to numerator and this will be 2h by mv. Now what you can do is you can just take the difference in the wavelength. See, it's getting very lengthy because I'm writing each and every step. When you're solving it on your own, you won't write every step. So then it will not take that much of time. It's 10h by mv naught minus 2h by mv naught. So that's 8h by. Let's see if it matches with it. 8h by. Yeah. So you have to connect this with the lambda naught. So this was lambda naught. Initial was this. So you have to connect it with this. So see, it is 4 times of this. So this is 4 lambda. If I call this thing as lambda naught, this and this is 4 times of this. So lambda 4 lambda. That's it. Note it down. And please don't just copy the solution. Note it down. Through this numerical, you will have an idea of collision also. So in any type of collision, these two equations are always valid. One is the conservation of momentum. Another is the coefficient of restitution. You can use conservation of kinetic energy only if your collision is elastic. But if your collision is not elastic, then kinetic energy is not conserved, but coefficient of restitution equation can still be used. But yes, for inelastic collision, E will not be 1, E will be less than 1, which will be given in the question. Adriel, is it clear?
Yes, sir.
Tell me once you have written, scroll it.
Done, sir.
So you can solve it using conservation of kinetic energy also, but will make the equations very lengthy. And just remember one thing, if balls are coming in opposite directions, they will take one as positive, so another one will be negative. Can I scroll it?
Yes, sir.
So, okay, so you must have written it here. So, this is about de Broglie habits. Let's stop here. The next class will start with probability effect. And please text the date of exam if you get your admit card on the operations number, on the number from where you get your meeting IDs and everything. Because if your date of exam is after 8th of April, we can have few more classes. We can cover few more topics. Otherwise, our last class will be on 4th, or I will take one more class on 5th. But if your exam is on 10th, then we can have 6th, 7th, 8th, we can have 2 or 3 more classes. Okay, so I'll stop here. We'll continue this in the next class. Huh? Sure. Bye. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Marita, can you just